Okay, so a couple more examples here. We're going to go, cancel that, and take a look at, using law of sines, law of cosines, and again, incorporating bearing problems, because I think those are great applications, but again, equally challenging. Okay, so in this particular example, it says, you're trying to get from city A to city B, but you are off course by 8 degrees. So if you, like you're trying to get from here to here, but again, instead of going in the right direction, like here, for some reason, maybe there was a wind or you're just off course, it went this way instead. So here's the airplane going the wrong direction, and all of a sudden he realizes, oops, I am in the wrong spot. I need to go to A. So I want to figure out like what angle do I have to turn, and then how much more do I have to travel? Okay, so, and again, thinking about that angle to turn, just like that last example, it's going to be the exterior angle, and it's labeled here very nicely. So, so at least I know that. So I'm looking there. Okay. So then it's 200 miles per hour. An error occurred after 20 minutes. So that means that's a third of an hour. And so a third of an hour. So if I do 200 divided by 3, to get that distance, that's 66 2/3 in terms of pen here. So this distance here I know is 66 2/3 miles, since it took me 20 minutes before I realized my error. So definitely not drawn to scale. And then this is this is 500 miles from A to B. Okay, and I know that's an 8-degree error. So automatically I'm seeing SAS. I can think law of cosines. And law of cosines would allow me to figure out this missing side length here, call that x, because it's opposite the angle that I'm given. So I'm going to use law of cosines first. I'm going to say, okay, x squared is equal to 66 2/3 squared plus 500 squared minus 2 times 66 2/3 times 500 times cosine of 8 degrees. And that'll give me at least x. Like, that'll give me how far I am, like from city B. So that's kind of like the second question. Okay, so 66 2/3 squared plus 500, plus 500 squared, and then minus 2 times 66 2/3 times 500, times 5,000, times 500, times cosine of 8, and then square root. So x is equal to 434.081. Okay, miles. Okay, so that's how far he is from city B. Now, the next question is this angle here, which is outside my triangle. This angle here would be its supplement, but it clearly, it's very, very obtuse looking. It's suspiciously obtuse. Can't really make that assumption, but if I'm going to find this angle and use law of sines, law of sines is going to give me its acute representation, because when you introduce the inverse sine function, you need both, but our calculator is only giving you the principal one. So it might be in our best interest to maybe find this guy up here first if I'm going to use law of sines, because that angle is guaranteed to be acute. I know it's acute because it's opposite a smaller side than the 500. So, and in fact, it's the smallest side, because we already know that this side over here is 434. So I'm going to actually solve using law of sines theta first. And then once I know theta and I know 8, I can figure out the question mark and then do its supplement. So I'm going to find theta first. So sine of theta divided by 66 2/3 equals sine of 8 degrees over what I just found, 434.081. So let's do that. Let's do sine of 8 times 66 2/3 then divide by 434.081, and we do inverse sine of our answer. And we get a very, very tiny angle of 1.223 degrees. 3 degrees, okay. Which means that I could figure out what this angle is and do 180 minus the 8 and minus this theta, and ends up actually, if you remember your honors geometry days, exterior angle theorem says that this exterior angle here would equal the sum of the two remote interiors. So if you know this is 8, you know that's 1, we could add it together to get that value of, question mark being 9.223 degrees. Okay. So again, good problem. And again, it illustrates the suspicion of using law of sines on an obtuse angle, because if I would have used law of sines on the obtuse angle, I would not have gotten this value, which is clearly obtuse. It's opposite that largest side there. Okay. Last example I want to do is number 5. Okay. And so it says a small aircraft leaves runway at a bearing of 30 degrees. So again, 30 degrees with respect to north. So it's heading kind of towards the northeast, I guess, mostly north though. So 30 degrees. And I always like to draw the trajectory just to show it. Okay, so that's 30 degrees, okay? After traveling for 1,200 meters, the pilot turns right 105 degrees. So again, turning to the right, if I think about, here we go. So here's the plane. So if I think about this plane going here, it's going to turn towards his right. So it's going to turn that way. And it's going to turn there 105 degrees. So that outside or exterior angle will be 105 degrees. So then, so I'll go to red. So, that was fun. So this angle here is this angle here is 105 degrees out there. And then I'm just going to continue that particular line. And then it's going to keep going, it says, until it's exactly east of where he took off. And so, in other words, I would right to that spot right there. So if that exterior angle is 105, that means this interior is 75 degrees. And we knew that this initial distance was 1,200 meters. And so I know that that's 1,200 there. And this is 75. If that's 30, then this is 60. And so I'm actually seeing in an angle, side angle case. So I don't need law of cosines. I actually need law of sines. Okay, what is the pilot's new bearing? So the new bearing would be if I would go where he's at and make just a north, south, east, west, or like here, compare him to north. So what is this angle? Here he is. What is this angle with respect to north? And so if I think about that angle right here, go another color. Looking for this angle right there, because that would be how far he is from north. And so again, looking at it from a triangle point of view, if this is 75 degrees and that's 60 degrees, I could figure out what that little tiny angle is there of the triangle, and think about like where that would appear on my particular diagram. Or I could also realize that he initially went with a 30-degree angle in this direction, and then he continued in this direction 105 degrees. So overall, his bearing should be 135 degrees. And again, thinking about like that, if this is 60 and that's 70, then this angle here is actually 45 degrees. And then if you slide that just a little bit over, oops, not you, this guy. Oh, okay. Okay, that's fun. This guy here. So if this is 45, we know that there'd be another 45 degrees of vertical angle. Its supplement would be 135. Okay. Now, how far does the pilot have to travel in this new direction? In other words, we're looking for x right here. Oops. I feel like now it's a little bit of a delay. Pen, what color did I pick? This color. Sure. X is right there. Okay. So again, angle, side, angle case. I know an angle. I know a side. I know an angle. Angle, side, angle is not ambiguous, which is nice. And so I could just say that the sine of 60 degrees over x, sine of 60 degrees over x is equal to the sine of 45 over 1200. Sine of 45 over 1200. And both of those sine values are values I know. So, because it does say like find an exact answer. So I could say 1200 times sine of 60, which is root 3 over 2, is equal to sine of 45, which is root 2 over 2, times x. So then that's 600. Root 3 is equal to root 2 over 2x. And then if I divide this over, so I get 1200 root 3 divided by root 2 is equal to x. Or if I multiply by root 2 over 2 to rationalize that, that'd be 1200 root 6 divided by 2 is equal to x. And then if divide one more time, that's 600 root 6 is equal to x. Now, I did say exact answer. If you want to know approximately how far away that is, 600 root 6, which is equal to 1469.694. I think we're in feet or miles? Meters. Okay. All right, very good. So I think that's the last example on this video. So hopefully the rest of the law of cosines problems make sense. Law of sines makes sense. Bearings make sense. If not, send me an email, and we can keep working through these together. Okay, very nice. Keep up with the homework and keep answering on Canvas.